So in this video we're going to start to develop the concepts behind solving sine equations, and we're going to start with the most basic sine equation that we can solve, and that would be an equation that looked like sine, and I'm going to call this theta 1 equals some side ratio a, and we're going to work off the unit circle for this first example. So the idea is that we know how to get, based on previous experience, theta 1 out of the sine function. We know that to get this angle we need to take the inverse sine of both sides. So we would get theta 1 equals the sine inverse of A. And we know that the sine inverse function has been defined on the interval from negative pi over 2 to pi over 2, or negative 90 degrees to 90 degrees. So if I work from a radian perspective, I know that my angle theta 1 is going to be some angle on the interval from negative pi over 2, or negative 90 degrees, to pi over 2, or positive 90 degrees. So if I think about what's going on, I have on the unit circle found a solution, an angle that gives me a side ratio of A. I have found a solution on the unit circle. I have found an angle theta 1 between negative pi over 2 degrees and pi over 2 degrees. So let's suppose we're in quadrant 1, we're between 0 and pi over 2 degrees. I have found an angle theta 1, and this is going to be an x-coordinate, which we don't care about. The sine of theta 1 equals A. Sine of theta 1 on the unit circle is the y-coordinate, so sine of theta 1 is A. That means A is the y-coordinate on the unit circle, and we found the angle theta 1 that produces that side ratio A. So what I want to recognize is that if I want all possible angles that generate a side ratio of A, I need to realize that I can rotate around the unit circle again and again and again, and every angle that's coterminal with theta 1, every angle that ends in the same spot as theta 1, will generate a side ratio of A. So this gives me a single solution right here on the interval from negative pi over 2 to pi over 2. But if I want all possible solutions, I need to get all coterminal angles. So the way that we do this is to get all solutions is we start off by saying, hey, I'm going to find the angle between negative pi over 2 and pi over 2 that gives me a side ratio of A. And we're going to call that angle between negative pi over 2 and pi over 2 the principal solution. I'm going to say, hey, you're the principal solution to my trigonometric equation. Okay? And then what we're going to say is, plus, if I'm working in radians, I want all coterminal angles, and what we have already learned is that to get coterminal angles, we just go plus 2 pi k, or if we're working in degree world, plus 360 degrees times k, where k is just any integer, 0, plus or minus 1, plus or minus 2, plus or minus 3, and so on and so forth. In other words, get theta 1 right here, and then rotate 360 degrees around the unit circle to get back to the same terminal side. Rotate 360 degrees, or 2 pi radians, you get back to the same terminal side. The solutions repeat forever and ever. So this gives me infinitely many angles that generate a side ratio of A. But that isn't the whole story, because on the unit circle, if we do one revolution around the unit circle, there is another place on the unit circle that gives us a side ratio of A. And the way that we get that is we reflect our angle theta 1, which is in quadrant 1, we reflect it over the y-axis, and if we do that, we get another angle right here. We'll call that angle theta 2. And theta 2 corresponds to an ordered pair. We're in quadrant 2, so when we reflect over the y-axis, we'll have the opposite of whatever x is. But a will still be whatever a was, because quadrant 1 and 2, the y-coordinates have the same sign. And this angle theta 2 is also an angle that gives the side ratio of a. And what we want to recognize is the relationship between theta 2 and theta 1. So when I reflect this point over here, I'm reflecting this terminal side over to a new terminal side, but this angle is getting reflected over. So this angle right here, the measure of it, that's the reference angle. The measure of that reference angle is going to correspond to the measure of this angle in quadrant 1. It's also going to be theta 1. And so what we see from that is that the angle theta 2 plus theta 1 are adding up to a straight angle, or 180 degrees, or pi radians. So theta 2, the second angle that generates a side ratio of a, plus theta 1, the first angle that generates a side ratio a, they are actually supplementary angles. They add up to 180 degrees, or pi radians. So theta 1 plus theta 2 equal 180 degrees, or pi radians. So if I want to get theta 2, this second angle that generates a side ratio of a, I just subtract theta 1 from both sides. So either theta 2 equals pi minus theta 1, because theta 1 and theta 2 are supplements, or theta 2, if we're working in degree world, is going to equal 180 degrees minus theta 1. So the way that we get our second set of angles that generate a side ratio of a is to take the supplement of the principal solution, theta 1, the principal solution for sine inverse of a, and then we're going to get all angles coterminal with this one by adding 360 degrees k, or 2 pi k, to this angle. So we get a second set of solutions, and they look like this. Theta 2, the other set of angles that generate the same side ratio, will just equal pi minus the sine inverse of a. Remember, this right here is actually theta 1, so we get pi minus theta 1. And then we're going to go plus 2 pi k, where k is an integer. If we're working in radian world, the solutions, if we're working, this is radian world. If we're working in degree world, then we would simply get, hey, theta 1 equals the sine inverse of a, where this gives us an angle between negative 90 degrees and 90 degrees, plus every coterminal angle, where k is an integer. Or you get theta 2, we get the supplement theta 2, which is just going to be 180 degrees minus the sine inverse of a, plus, hey, we need all of the coterminal angles. And I did a quadrant 1 example for theta 1, but we'll get supplements even if we're in quadrant 2. So for example, if you do sine of theta 1 equals a, and then you solve, theta 1 equals sine inverse of a, and this angle theta 1, we know it's on the interval from negative pi over 2 to pi over 2, so it could be the case that theta 1 is sitting down here in quadrant 4. So theta 1 could be an angle here, and you would have the x-coordinate and a on the unit circle. This sine of theta 1 is the y-coordinate on the unit circle. So to get a second solution on the unit circle, you'd reflect over here into quadrant 3, and the x-coordinate would be the opposite of what it was, but the y-coordinate's going to be the same. And so we reflect over and get this new terminal side. So here theta 2 is a second solution on the unit circle. But notice when we reflect, this is going to be theta 1. And theta 1 right here, this is it's going to have the magnitude of theta 1. Theta 1 is a negative angle because this represents a clockwise rotation. So for example, theta 1 might be negative 45 degrees, which means that this reference angle right here is going to be the absolute value of theta 1. It's going to be a 45 degree angle here. And what I want to notice is that theta 2, if this is a 45 degree angle, this angle right here is going to be a 225 degree angle. And when we add it to theta 1, which is a negative 45 degree angle, it's going to knock off this little slice and give us 180 degrees. So it's going to work whether our angle is positive or negative. So let's look at a concrete example. Let's say we're solving the trigonometric equation sine of theta equals 1/2. So we would start off, and let's do this in radian world. Now we'll do it in both worlds. We'll separate the screen, and we'll say, hey, let's work in radian world, and let's work in degree world and see how this plays out in both worlds. So degree world, radian world. So I'd start off and say, hey, I know that there's going to be a principal solution. I'm going to say I'm going to go hunting for theta 1, the principal solution. And if I'm in radian world, I'm going to start off by taking the sine inverse of both sides. And I'm going to get theta 1 equals the sine inverse of 1/2. And the sine inverse of 1/2, because this is the principal solution, the solution the calculator would give you, it would have to be an angle between negative pi over 2 and pi over 2. So up here I've graphed the sine of theta, and I've also graphed the line equals y equals 1/2. So everywhere where y equals 1/2 intersects the sine of theta, I get an angle at which the sine of that angle is 1/2. When I take the sine inverse of 1/2 and I get theta 1, theta 1 has to be an angle between negative pi over 2 and pi over 2. So theta 1 is going to be this angle right here that's producing this ordered pair that's on the interval from negative pi over 2 to pi over 2. This tick mark here would be 1/2. So this is the principal solution, and what I can see is this is to the left of the crest, and over here to the left of the crest there's another solution, and to the left of the crest there's a solution here. These are the coterminal angles with the angle theta 1. So to get these other intersections that are to the left of the crest of the sine function, I'm going to have to add on plus 2 pi k to get the coterminal angles. Notice that misses everything that's to the right of the crest. And we'll go hunting for those in just a second. So if I continue to push this through, I would get theta 1 equals, hey, what is the sine inverse of 1/2? Well, I need to think about the unit circle. So on the unit circle, between negative pi over 2 and pi over 2, if I have a 30 degree angle or a pi over 6 radian angle, 30 degrees, or pi over 6 radians, that corresponds to the ordered pair root 3 over 2 comma 1/2. So 30 degrees or pi over 6 radians is going to be the angle that generates a side ratio of 1/2. So using my special angles, I see that sine inverse of 1/2 is just going to be pi over 6. And then to get the rest of the angles, I just add on 2 pi k to get the coterminal angles. If I were working in degree world, everything would be playing out exactly the same. I would just get sine of theta 1 equals 1/2, and then I would take the sine inverse of both sides. But I would recognize that this is the principal angle. It's between negative 90 degrees and 90 degrees, still corresponding to this one. Here's theta 1. He would be at, he'd be right here between negative, instead of, it would be negative 90 to 90 on for the tick marks. And then to get all the coterminal angles, I would go plus 360 degrees times k equals, hey, the sine inverse of 1/2 on the interval from -90 to 90 is going to be 30 degrees. So I replace that with 30 degrees, and I go plus 360 degrees times k. So this gives me half of my possible solutions, and then I need to recognize that there's another angle here, theta 2, that is the supplement of theta 1. So we know that theta 2, the other solution, has to equal either 180 degrees minus theta 1, so that we get, because theta 2 is the supplement of theta 1, or theta 2 is going to equal, what's it going to equal? It's going to equal pi radians minus theta 1. But that would only give us this angle right here. To get these other ones, we would need the angles that are coterminal with theta 2. So to do that, we would get plus 360 degrees times k, or plus 2 pi radians times k. And then we would say, hey, what is theta 1? Well, theta 1 is this pi over 6 angle, so we get pi over 6 minus, you get pi, right here, pi, minus theta 1, but theta 1 is the pi over 6, plus the 2 pi k, and then we would get a common denominator, minus pi over 6 plus 2 pi k, which would give us 5 pi over 6 plus 2 pi k. Or if we were in degree world, we would get 180 degrees. That's a horrible 180 degrees. We would just get 180 degrees minus 30 degrees is theta 1 in degree world, plus the 360 degrees k, equals 150 degrees plus 360 degrees times k. And in all of these cases, all 4 of the cases, we know that k needs to be an integer. So 0 plus or minus 1 plus or minus 2, and so on and so forth.